All right, folks, welcome to another one-day unit, and today we're going to be talking about relativity. This is a good unit to spend just one day on. A lot of the concepts are very broad, but easy to digest in general. Even so, I'm going to take this one step further than most high school physics teachers do. Most high school physics teachers will tell you about relativity and what happens as a result of it, but very few actually explain why it is you see some of the crazy things that we're going to be talking about today. So, let's dive in. This is your standard thought experiment when we're talking about relativity. You've got two twins here, and you got this guy and this guy, and this one's the more adventurous of the two. So he bids goodbye to his twin, and he goes in the spaceship out into space, flying at speeds, not too far away from the speed of light, and he hangs out there for a long time, maybe 20 years, and when he comes back to Earth, he will have aged less than his twin. This sounds crazy, but it's legit. This actually would happen. Yes?
Isn't that because, in space, time is, a lot, I don't know if you consider it longer or shorter, but, a couple minutes in space is, way longer on Earth, right?
Yeah, it depends how fast you're going, and that's exactly what we're going to get into. So, yeah, I'm going to lay the foundation here, and then we're going to see some of the insane things that occur. And this is one of the side effects of those. So, to just kind of lay the foundation here, this is water. Remember when we used to talk about waves and things like that? Remember how in order to get water waves, you need water. Without water, you're not going to have water waves. Without air particles in the air, you're not going to have sound waves. So there are many things in terms of wave behavior that require something to travel through in order to exist. You're not going to get sound waves without air. You're not going to get water waves without water. That's why if you're in space and you try and scream as loud as possible, nothing is going to come out. Your vocal cords will be flapping back and forth at whatever frequency you normally speak at, but because there are no air particles in the air to vibrate against and to make things vibrate, you're not going to hear anything. So it doesn't matter how loud you try and scream in space, nobody is going to hear you. Now, everybody kind of thought this also applied to light, because light exhibits wave-like behavior. That was the entire purpose of the chapter, Light is a Wave. And so we know that it behaves like waves in all sorts of different ways. So naturally, people thought that light needed something to propagate through in order to exist, just like water waves need water and sound waves need air. And they called this stuff, a fancy name here, luminiferous ether. And they believed that the Earth and the solar system and the universe was just, it contained all of this stuff here. And the Earth was passing through it, and the sun was passing through it. That's the reason we could see the sun, because without this ether, the light rays would not have anything to move through in order to make it to the Earth. So this was just kind of taken as fact for hundreds of years, and it wasn't until these two guys, happy-looking gentlemen, decided to come around and test this to see if it they assumed it was true. They wanted to figure out how fast the Earth was moving through it, and they did that through an experiment. So basically, this is kind of a primitive laser. It's not like we know them now. It was basically a box with a tiny hole at the end that light would come out from, but it's not like, a laser pointer or anything like that. And the light would come out, it would hit this half-transparent mirror. Some of the light would bounce up to this mirror and then go down and go through again and land on this screen. Some of the light would pass through this half-transparent mirror, and it would hit this mirror, and then it would bounce back, go down, and interact with the screen down there. And based on the pattern that showed up, you'd be able to tell which of these two paths of light reached it first. And you could make other deductions from that too. hopefully, in their case, they wanted to figure out how fast the Earth was moving through this stuff. Because, if you think about it, if the ether is moving in this direction, it's going to take a long time for the light to travel in this way. Because it would be like, trying to walk through, water that's traveling in this direction. You're going to go a lot slower than when you're going with the current or neutral to it. So the main thing is you should have gotten a pattern here that showed the two beams of light arriving at different times. And so it was a very fancy experiment. This is just another setup here. And what they found is that regardless of the setup, how they angled it, or where they took it on Earth, it always gave a null result. It always showed that both beams of light arrived at the detector or the screen at the exact same time. That's totally not what they were expecting. And basically what it showed then is that the Earth is not actually passing through any luminiferous ether or anything else. And this was one of those things that really shook the foundations of science because, for 200 years, people believed that light needed something to propagate through. It was just assumed to be true. And until they finally tested it, they realized that light is actually extremely special. And you're going to see exactly how special it gets, most notably the speed of light. So, speaking of that, there is no luminiferous ether. Subsequent experiments had failed. And now it's just kind of known that light does not need something to propagate through, not just because it behaves like a wave, but because in essence it is a particle in and of itself. But in order to continue with this, and in order to see why it is that if you and your twin separate and you go out into space and he stays home, why it is that you age less, you have to understand where I'm going to go in the next 5 minutes here. So let's see if we can do this. If I lose you, please let me know. This is the type of discussion that you're not going to see again unless you end up taking a second-year university physics course. So let's see if we can follow along. It's understandable. You just got to do your best to stick with me here. All right. So that's more or less the path that red ball is taking there. Now, you're observing that ball go up and come back down. And this is from a certain frame of reference. Right now, your frame of reference, when you see this happening, the ball is in the pickup truck, it's launched, and then it comes up and it comes back down to the same location. You're seeing this as an observer apart from the truck. You're separate. You're out there. You're not on the truck. And that's your frame of reference. Now, let's say we wanted to figure out the speed that this ball had here. Speed is just distance over time. So we would take this distance here and divide it by time, and we'd get a certain number. Let's just assign it a random number. What's a good number for speed? 17. 17.38 meters per second. Or miles an hour, whatever. So that's our speed. Now, let's say you are instead in the back of the pickup truck. And you observe this ball go up and come back down. So we'll just say that you observe it go up and come back down. If you're in the back of that truck, will you see a parabolic arc like when you're apart from the truck, like you guys are? No, of course not. You're just going to see it go up and come back down because it lands in the same place. If you're riding along here, you're just going to see it go up and come back down. Now, which of these two distances are greater? This black parabolic path or this path in blue where the ball would go up and come back down? I'm not trying to trick you. The black path would be the longer one. So, if this path is longer, and we wanted to, say, calculate the velocity from when we're in the back of the pickup, we would use the same equation. Velocity is equal to distance over time. But this distance is going to be a bit less. Would we measure the same time? Also not a trick question. Yes. If you had a stopwatch and you're sitting in the back of the pickup truck and you measure how long it takes to go up and come back down, you'll get the same time as if you're measuring it apart from the truck. So this time stays the same, but the distance is going to be a little bit less, and that would give us a smaller velocity if we're measuring it from the back of the pickup truck. So we'll just say 12.38. All right. Are you still with me? Any questions up to this point? Because we're like almost right there on figuring out why such crazy things happen with relativity and time here. Okay, so we're going to take this one step further now, but it's the same scenario. Okay. This is the type of picture that you'll see if you end up taking a class called Modern Physics in college. It's a class where they kind of talk more about relativity. I still have my textbook, actually. It's got pretty much this exact same picture in it. And it's the same scenario. The only difference is instead of a ball going up and coming back down, this, we have to imagine, is a beam of light. So the beam of light is going to go up, it's going to hit this mirror and come back down. Now it's on this train here. And this is a super fast train. Like, unrealistically fast. It's going so fast that you can actually see the beam of light, and that beam of light takes a path kind of like a triangle there. So, of course, if you're on the train, you're going to see the light go up and come back down. But if you're apart from the train, just like when you were apart from the pickup truck, you'd see it take more of a triangular path here. So let's do that equation again. So if you're standing on the train and you see the light go up, hit the mirror, come back down, and you could somehow time it because you're just that good. You have that good vision and you've got a really, really good stopwatch and you measure it out. The speed of light that you would measure is this number here. 3 times 10 to the 8 meters per second. The speed of light is extremely fast. It would go all the way around the world 11 times in 1 second. That's how fast light travels. Now let's go down to this example here. So this corresponds to A, and this is going to correspond to B. So for letter B here, it's the same equation, distance over time. Would we get a greater velocity or a smaller velocity? It's kind of the same story as the pickup truck. You know, we're traveling a greater distance, and we'd think that we'd have the same time here. So let's just say, you know, if we have the greater distance divided by the same amount of time, maybe it would be 5 times 10 to the 8th meters per second. Sound reasonable? There's a problem here. We have just broken probably the most important, maybe the most important law in physics. And that law is this: nothing can go faster than the speed of light, and nothing can be observed to go faster than the speed of light. So this number cannot be bigger than this one. You will never ever see light going faster than 3 times 10 to the 8th meters per second. That is like the fundamental law in terms of motion and physics. So there's a bit of a pickle here that we have to resolve. If this isn't true, then something must change about this equation here. Now, this is a greater distance. We cannot dispute that. So this is going to still be the same. But if this number cannot be any greater than 3 times 10 to the 8th, the only thing that could change is time. And that is what changes. This is why we see such crazy things that you're going to see up here shortly in terms of relativity. This is why time basically turns into something that is not solid anymore. It can be sped up. It can be slowed down if you have the right conditions. And you'll see some of those today. Questions on this? So this is why time gets messed up. Because nothing can be observed going faster than the speed of light. Therefore, when you're calculating speed, distance is distance. You can't change that. But time is the one thing that can fall apart here. And essentially, it does. Time, what you would observe here then, just to give you an idea of what you'd see here. So this guy would see the amount of time it takes as regular. But this guy would observe this beam of light taking more time to go up and come back down as opposed to this guy. If you're standing on the train and you see this happening, maybe you measure 0.4 seconds for that light beam to go up and come back down. But if you're apart and you see this happening over that greater distance, maybe your stopwatch would measure 0.7 seconds. I mean, this is a crazy high number for that amount of time, but you get the idea. So here's some of the effects of this. This was just the foundation. Now on to the more flashy stuff. And this is something I basically just said. Everything in terms of the speed of light is the same regardless of what is happening. If you take a flashlight and you shine it, that beam of light is moving at the speed of light, 3 times 10 to the 8th meters per second. But if you're running with that flashlight and you shine it, it is not traveling at the speed of light plus however fast you're running, because nothing can be observed to go faster than the speed of light. That law can never be broken. And it talks about reference frames too, and I'll get more into that as we go forward here. So time can be bent. It can be sped up and it can be slowed down. If, like in the example from the train, you are moving very quickly, time goes by more slowly. That's why you had a bigger number on the bottom of the screen there. If you're not, if you're holding still, time moves normally or faster, depending on which frame of reference you're looking at. Now, if you are the person that time is slowing down for, like if you're the one moving really, really, really fast on that train, and you're looking at your watch appears to be working just fine. It does not appear to slow down. It is only once you look outside your frame of reference that you notice something funky happening. If you're on that train and you could see a clock at the train station go by, you would notice that clock is moving faster than it should. On the same note, if someone's at the train station looking at your watch or your clock on the train, he would notice that that clock is moving slower than it should. So everything appears normal to everybody in their own frames of reference. It's not until you look outside that things get weird. So yeah, it does not appear to someone in the object that time is slowing down. Time appears to slow down for extremely fast-moving objects. And you can actually prove this. If you take an atomic clock and you synchronize it with one on the ground on Earth, and you stick one on a Boeing 747 that flies all around the Earth, in a year because it's an airline, and then you take a look at both clocks after a year, you will notice that they have two different times. Now, it's not super noticeable. It might be, 0.0001 second difference, but there is a difference in the amount of time that both clocks measured. It is measurable. And just to put a visual to this, you got a nice F22 right here. And we're going to say this is even better than a standard F22. It's kind of hard to imagine that, but both the ground and the airplane will say register a time of 3 o'clock at takeoff. Then the super F-22 flies around at, I don't know, maybe like 50% the speed of light or something like that for 15 minutes according to the pilot's time. So if 15 minutes have elapsed for the pilot, more time will have elapsed on the ground. If the ground people could see the clock inside the aircraft, it would appear to them that the clock is moving slower. But to the pilot, it appears to be moving normal. But if he looks at a clock on the ground, it's going to appear to be moving faster than it should. It's all about these different frames of reference. Yeah. Sure.
Like I understand it, but like if you actually look at the clock, it looks slower.
Yeah.
Or faster.
If you could. Now the thing is, in order to actually see this effect, this does have to be going at like 30%, 50% the speed of light, which isn't reasonable, and you wouldn't be able to see it anyway. But it would actually happen, and you would register this if you could actually see something like that. And we actually have equations that we can apply to this. And this is on your formula sheet. So let's go ahead and just take a look. Let's say that the pilot registers 1,000 seconds have elapsed according to his watch. And he's flying at 90% the speed of light. So you can actually figure out how much time has elapsed on the ground. You just plug numbers into this equation here. This change in time with a little p next to it, that means time proper. It's the amount of time that's elapsed for the pilot there. So that's 1,000 seconds. 1 minus v, which is your speed, divided by c, and that's your speed of light. Both of those are squared. And because we're going at 90% the speed of light, your velocity is 0.9 c. So it looks like, oh, that 2 should actually be a square. I got to change that. So that should be a small 2 up there. So yeah, plug those numbers in, and what you'd find is that on the ground, over 2,000 seconds have elapsed. So yeah, it all has to do with these different frames of reference. If you're the one moving really, really fast, then you're the one that's going to benefit from this because less time has elapsed for you. Time essentially has slowed down for you, even though you don't notice it in your frame of reference. But if you look outside of it, you'd see time going quicker. So if you have to pick that you'd be the person that's going really, really fast. Now, a couple other interesting things occur when you start to approach the speed of light, or different percentages of the speed of light. Not only does time get bent, not only does it get stretched and compressed, but length also does. And if you have an object that is moving extremely fast, the more that contraction is going to appear to be. And this only occurs in the direction of the motion. So let me just show you what I mean here. So this is a sand tiger shark. If you've ever seen a big shark like this at an aquarium, chances are it is a sand tiger because they do very well in captivity. Usually very harmless unless you punch it in the face. So yeah, you'll probably see one of these around at some point in your lives if you go to a big aquarium. Now this is a very special sand tiger. They're also called ragged tooth and gray nurse sharks depending on where you are in the world. But if you're going at 50% the speed of light, when I say length contraction, I mean the length is going to contract. At 50% the speed of light, it's going to appear compressed. Yes?
Is that why, when people get back from, space, their spines are all messed up?
No, that has to do more with gravity and pressure. A good observation, though. That's true. I think in space you actually get in space you get longer. because gravity kind of compresses your spine, but it would expand more in space when that pressure isn't there. So the shark would compress a little bit, and the faster you go, the more compressed it would appear. So if it's moving at 90% the speed of light, it would look like this. And if it's moving at 99% the speed of light, it would look like that. Now, this does not mean that the shark feels super compressed. The shark appears normal within its own frame of reference. That's kind of one of the themes here. Within this shark's frame of reference, it appears normal. If it was taking its own measurements, it would appear to be 5 meters long, or 15 feet. But it's when we're looking at the shark, as it's streaking across the sky at 99% the speed of light, that it looks like this. Now, what do you suppose the shark would see if it's looking outside its frame of reference to the Earth? Yes?
It's like really big.
Yeah, exactly.
That's in like movies and stuff where like the guys.
Yep, that's actually legit science. Things get stretched out if you're the one moving really, really fast. Everything appears to get elongated. So this shark would appear to see you guys as very bloated high school students because you'd appear more stretched out. And you can actually calculate these numbers. It looks like I got to change this number to a square as well. It's comforting to know that I haven't changed this in probably like 10 years. So definitely going to correct that. So yeah, you can actually calculate it out. 5-meter shark, and you can figure out exactly how long it would appear to those of us on Earth. And if it's going at 90% the speed of light, you plug in those numbers just like we did in the other example, and you get 2.18 meters. That's its perceived length, how long it would appear to us on Earth. You'd also have an increase in momentum. Obviously, the faster you go, the more momentum you have because the velocity increases. But when you're increasing momentum and you get close to the speed of light, then it increases basically exponentially. And you would use that equation to figure it out. One of the common misconceptions here is that it is as though your mass is increasing, but it's not really your mass that goes up as you approach these speeds. It is your momentum because it is all dependent on your velocity. So you can kind of think of it like this. If this is your normal little, playground train there, if it approaches like 50% the speed of light, normally you'd think it would be, if we're calculating momentum, mass times velocity, and you have the correct velocity there, it'd be a certain value. But in reality, it would appear to be moving that quickly, but a lot more mass. Therefore, much more momentum. So at 50% the speed of light, it would be like a gigantic, steam train, and at 90% the speed of light, one of those fancy bullet trains that they have in Japan. So yeah, momentum does increase a dramatic amount, and you could run through that same calculation and get another number there. Okay, you guys heard of E equals mc squared, right? Okay, good. So the interesting thing about this is that, what do you suppose E stands for?
Energy.
Energy, absolutely. What do you suppose M stands for?
Mass.
Yep. What do you suppose C stands for? Speed of light, absolutely. So energy is equal to mass times speed of light squared. And where we ultimately go with this is rest energy because it does not take a velocity into account. So in your body and in my body, if you multiply your mass by the speed of light squared, which is just an enormous number, you're going to get an enormous amount of energy. So this is really measuring the amount of energy present molecularly and atomically in your body. If you were to harness all the energy in all the atoms of your body, that's where that gigantic number would come into play. The only time you're going to release that amount of energy is if you are, using nuclear energy at a nuclear power plant, or if you are creating an atomic bomb or a hydrogen bomb. Those are the only cases where we start to release these orders of magnitude of energy there. You cannot produce, a zillion joules of energy just by standing with the mass that you have. Thank you very much. Oh, there you go. Hey! How did I get this? So that's nuclear physics. Okay, we got 10 minutes. This is going to be a fun 10 minutes. Total energy also goes up. We've got Sonic the Hedgehog here, and if he is approaching like the speed of light, you can actually calculate his rest energy plus his kinetic energy, and you can do it with the same equation. It looks kind of like this, just like the other equations that we've dealt with up to this point. It looks like I actually have the square correct on that one. Good for me. So he's 25 kilograms running at 90% the speed of light, and you would end up with this enormous amount of energy there in joules. And this is much larger than if you just multiply his mass times the speed of light squared. Yeah, isn't he awesome? That was like, his movie was the last one I saw in the theater before the pandemic started. So
yeah, I just saw that. Okay, is it Oscars? That's the movie one, right?
I think so.
Okay. Yeah, I saw like all the movie nominations for like this year, and it's I don't know any of these.
I know that sucks about that. Yeah.
Yeah.
But yeah, I finally did see another movie when I saw Mortal Kombat the other day. That was fun.
How was that? Is that good?
I enjoyed it. Very violent, but it was a good story. It was fun. I liked it. Okay, so let's take a look at general relativity then. So everything that we've been talking about is special relativity. And that's kind of under the tent of general relativity. So when I say length contraction, time dilation, and all those other things, that is special relativity, and that occurs because of general relativity. And as you probably guess, Einstein came up with all this stuff. And just to get you started on general relativity here, how many people have heard of the space-time continuum?
Yeah.
Good, most people. So basically, you can think of it as a bed sheet.
Whoa.
One axis is space, the other axis is time. And it simply means they're related. If you do something to mess up one, you're going to mess up the other one. So if you think of it like a bed sheet, and you're holding it at the four corners, and you put a large mass in the middle like a bowling ball, it's going to bend that bed sheet an awful lot. So you're going to mess up space and time an awful lot, as opposed to if you just throw a marble or a tennis ball in there. So here's where this comes into play. The bigger the mass you have, the more it messes up the space-time continuum. Man, that's just fun to say. So let's say you have a star which has a lot of mass, and an object is traveling through space. That mass, because it's bending the space-time continuum, because it has gravity, it is going to bend that object in a different direction from the straight line path that it was originally going. And this also is something that can occur with stars. Let's say we have a star, and it's located right up there. And the light is traveling in this direction. And it passes by the sun in such a way that the sun bends the beam of light, because it's just following the bend of the space-time continuum. Well, do you remember a while ago when I said that when light goes into our eyes and into our brains, that we automatically assume it's been traveling in a straight line forever? So, if we assume this light has traveled in a straight line forever, it appears to us to be located here in space. But in reality, it's over there. It's kind of interesting to think about. Now, this only occurs if you have a big mass between you and whatever's producing that beam of light. So when you look up at the night sky, those stars really are where they appear to be, for the most part. But if you have an object like a star that's, right on the edge of where the sun would be, maybe you see it during a solar eclipse, you might see that star in a different location than it actually is. Kind of interesting to think about. It's called gravitational lensing. And here's an example of it. So you can see there would be a big mass right here, like maybe a galaxy or something, and it's messing up the light that's coming from all around it. And you can see it as kind of a halo effect right here. And I'll show you a better picture of this, because we're going to talk about black holes. This is an image that was actually computer generated on what would happen to light from a galaxy if a black hole passed in front of it. So the black hole's in the foreground. It's not like annihilating the galaxy or anything. But that's what would happen with the light. The light bends from the enormous gravity produced from the black hole, and it kind of messes it up like that as it goes around.
So are these things like real?
Yeah, black holes are real, for sure. And now I'm going to tell you what happens if you fall into one. So let's say that there is a black hole in the back of the room. And there's different kinds of black holes. There's big ones and there's little ones. We'll say this is a little one. Let's say we take the Earth and we crush it down to the size of your fist. The Earth would then be a black hole. A black hole is produced when you have something that's simply so dense that it produces enough gravity that light can't even get away. So if we do that to the Earth, you'd have to crush it down to about the size of your fist or a baseball or something. Now, to figure out what happens to you, you got to know that right now your feet are being pulled to the center of the Earth more than your head. Because the further away you get from Earth, the less gravity is going to affect you. Now, you don't really notice this change because it's very minute. But if you have a black hole the size of your fist, that gravity difference is exponentially larger. So let's just say you dive in to that black hole. Guess what's going to happen? The tips of your fingers are going to be pulled a lot more strongly than the rest of your body. More specifically, the molecules on the ends of your fingers are going to be pulled more than the rest of your body. So what you're actually going to see is something that's legit called this. It's called spaghettification. The molecules from your body would spaghettify into these tiny strands going into the black hole. You'd look like these little bits of spaghetti, minute, very thin pieces of spaghetti going into that black hole, and that's how you'd die. Your body would just be ripped apart because of that gravity difference. It's so enormous that it would pull this part of your body way stronger than the back part of your body. And you'd be pulled to shreds almost immediately. So it only hurt for about a split second. But that's how you'd go. Now, this is different compared to if you fall into one that is much larger. The middle of galaxies, ours included, the Milky Way, has a black hole there. And they're enormous because they're constantly feeding on the higher density of stars that exist in the middle of galaxies. So it's just enormous. And what that means is that if you get close to it, that gravity difference is not nearly as strong. So you'd fall in just fine. But this is where some more interesting things with respect to time happen. Not only does time slow down if you go super fast, it also slows down if you enter a very strong gravity field. So think of it like this. You're falling into this black hole. And just like the example with the frames of reference, everything's going to appear normal to you, according to your watch. But if let's say someone is watching you fall into this black hole from the Earth, and they can see like a clock. Like this is, maybe you're like Flava Flav, and you've got that gigantic clock, okay? And if you fall in with that clock, people on Earth would notice that as you go deeper and deeper into that black hole, that clock gets slower and slower and slower. Now, according to you, it appears to be running normally, and it appears to be going just fine. But of course, what do you suppose you're going to observe when you look outside your frame of reference to the Earth? Yeah, everything is going to be speeding up faster and faster and faster. So again, it's all about frames of reference. If you're in the black hole, everything's going to appear to be normal to you till you get crushed and die. But time-wise, everything's going to seem just normal. But if people watch you falling in from that separate frame of reference, it's going to appear to them like time has slowed down for you. And when you look outside, as you fall in, time is going to be going faster and faster and faster. It's crazy stuff. Now, the last thing I want to mention here with these last 40 seconds, just stick with me. You've heard of wormholes. Chances are, well, from everything that we've seen, our galaxy is flat. It is not negatively curved. There are three ways your galaxy could look. Ours is, from all measurements and indications, it's flat, it's not curved. But if it happened to be curved, people say maybe you got a black hole here and a black hole here, and they could link up and you could go to different parts of the universe. Maybe, but you would not survive because you're falling into a black hole. So your little atoms in your body would make it to the other part, but you would not because you'd be dead. So if anybody says, let's go through a wormhole, just say no.
Through the wormhole with Morgan Freeman type thing?
Right. Have a good day, folks.
You too, you too.
Thank you.
Bro, I actually did this